Okay, hey everybody. Our goal here is to get to the Chi-Squared test, but it's really important that we kind of do some big picture stuff first. And the thing that I want to focus on is what does it mean when I say, is this statistically significant? This phrase happens a lot, and sometimes it means something, and sometimes people are like, I feel like you're speaking gobbledygook. It doesn't really make sense to me. So here's an example of what I mean when I say that. Let's talk about trees. So statistically significant, I really like this phrase. This is from Mr. Youngsaver, who had that video that we watched the other day. But like in a world where trees are this tall, right? Like most trees are this tall. They're kind of short. They're not really that big. But, you know, there's always some variation. How likely is it that we would find this one? Well, if this was your average tree, here's like a kind of tall tree, but it's not like that unusual. This would probably be a thing that you would run across and not be too surprised about. But this one is remarkably tall. It is exceptionally tall compared to the average tree. And this is one that we would probably call statistically significant. It is very much beyond the pale. Another example be like this. In a world where M&Ms are an even mix of color in each bag, so this is what you expect. If you opened up a bag and it was all red M&Ms, you would be pretty surprised. That would probably be an example of a statistically significant bag of M&Ms. Whereas if you just had one like somewhere in the middle here that had a couple more red M&Ms, you're like, wow, there's a lot of reds in here. That is maybe iffy on the statistic significance. Okay. Before we can really get to Chi-Squared, we have to talk about degrees of freedom. If, for example, I said I need three numbers that are going to add up to 10, you could be pretty wild with what you pick. Maybe you go 2 and then 17, and then all of a sudden, it doesn't really matter what I put here. I could have put any number here, any number here. At this point, though, I'm stuck. If the sum is going to be 10, I have to pick -9 because 2 and 17 gets me to 19. Now I need a -9. That -9 was fixed. This means I had degrees of freedom of 2 because I got to pick two different numbers. If you had 4, then obviously, okay, so I can go 1, a 7, a 32, and now because I've gotten, so 1 and 7 is 8, 32 is 40, this is going to have to be a -30. I had, again, in this case, degrees of freedom 3. You can imagine when we get down here, I would have degrees of freedom of 4. I could pick the first 4, or this any 4 really, and then the last one, whatever I have, I would have to select. So I have increasing degrees of freedom. And you'll notice in this case, it is the number of numbers, I guess, -1. So in this case, it was 3 minus 1. In this case, it was 4 minus 1. In this case, it would be 5 minus 1. That pattern would hold. When we get into tables, it gets a little bit messier. This is a two-way table where I know that the top is going to sum to 26. This is going to be 40. This will be 18. This will be 32. And I have a fair amount of choice in where I put things right now. Now, there are some restrictions, like I can't put a 20 here because then I won't sum to 18. So these two numbers do have to be less than 18. But I can start in a lot of different places. It doesn't really matter. Let's, in fact, start with over there with that 18. Let's say I'm going to have a 10 right here. Now you'll notice I had 4 spaces to fill in. If this is 10 though, I have only one choice for this. So this is no longer a choice for me. I have to put 16 here. And since I have 10 here, I also don't have a choice here. This has to be an 8. And voila, I also don't have a choice here because this one has to get me to 32 or this one has to get me to 40. I have to put 26 here. So in this case, in a 2x2 table, 2x2 table, I have degrees of freedom of 1. When you get to a 3x3 table like this, I have a fair amount of choice. Again, I kind of got to pay attention to that. You can't go here's my smallest number is a 25. I got a bunch of 25s. I can't put something that is more than 25 here, but we could maybe start out with let's call this one a 10. I still have a lot of choice, right? I can put in numbers here or here and over here, so I can still have more degrees of freedom. Let's put another 10 up here just for funsies. Ah, shoot. Now this number is stuck. I have to pick 5 here. There's no other choice. So that one, I'm going to make green, so I'm leaving my degrees of freedom as white. Okay, but I still have some choice over here. I haven't totally cut myself off here. Okay, where else can I put a number? Let's see. Here's my 30. Let's go up here. We'll go with an 8 here. That's going to force this one to be a 17 or a 7 because I know how to add. No worries. It's cool. I still have one more choice. Okay, cool. Let's go with a 9 here. That'll get me an 18 here, and then I'm forced to pick, so 18 and 5 gets me 23, so I'm going to need a 27 over here. 27 and 7 would get me 34, so I'm going to need a 6 here. Okay, notice in this case I had 1, 2, 3, 4 degrees of freedom, and this was a 3 by 3. And you might notice a little bit of a pattern here. It's a pretty small one thus far, but it is one that will actually hold for us, is that in a 2 by 2 table, we have 1. In a 3 by 3 table, we have 4. In a 4 by 4 table, we would have degrees of freedom of 9. And really the rule here is that you would take the number of columns minus 1 times the number of rows minus 1. So if I had like a 4 by 7, then that would lead me to degrees of freedom of 3 times 6, or degrees of freedom of 18. Okay, so why do I care about degrees of freedom? This is why. So this is a chi-squared graph. You have a link to bring you to this Desmos graph. It is very similar to a normal graph in that the area underneath this curve right here is 1. But the curve changes based on the degrees of freedom. So right now I have it set at 5, but I'm going to let this little video here play. And what you're going to notice is that as the degrees of freedom get to be larger, this kind of flattens out. As they get smaller, it comes closer here, and it kind of changes according to that. Now, what I care about here is the value, and it's going to be what we call the chi-squared statistic. And if I end up with a number like 4, notice 4 is sitting pretty happily in this curve, and right now I have 5 degrees of freedom. 4 is sitting happily in this curve. That would not be statistically significant. Over here, depending on where my metric is, and we've talked about this before, right now it is about 9%. This R value is controlling that. If I had a test statistic of 10, then that would fail, or it would pass, I guess, the 9% statistic, where this is less than that, meaning that it is a rarer and rarer instance, right? So what you're going to see here is, we can start playing this again. You could set that statistic wherever you want, right? That red bar is changing. I'm going to move it down now where it's about 5. And now this 5% statistic, so you see that it's, oops, sorry, wrong thing. The 5% statistic is here. That means that with 5 degrees of freedom, where this is set right now is about 11. It is saying any number that is more than 11 is going to be statistically significant. It would like pass that test, or saying like this is such an unusual result, right? Results over here are not that unusual. Results over here are far more unusual. So let's look at an example for chi-squared and see if we can make sense out of this. We'll come back to this graph. So this is how you'd actually calculate the chi-squared statistic. This is the chi-squared, and it is pronounced chi. Is that you would take the sum of the observed minus the expected squared, and then divide by the expected. What do I mean by that? Let's use this example of a die is thrown 120 times with the following results. So I got a 1 27 times, a 2 12, a 3 16, a 4 25, a 5 26, and a 6 14. So this is what we call our observed. This is the frequency. Now, this isn't so bad that I'm like, yeah, this is definitely a weighted die, but I definitely got like way more ones than I got twos, and 120 is like a fair large number of times. So how unusual is this, really? Like in a world where this die is fair, how likely is this? That's the question that we're asking. So to calculate the chi-squared statistic, here's what we're going to do. First of all, we need to know what is expected. If the die is fair, I should have gotten 20s all the way across the board. I know that's not perfectly going to happen, but I should have gotten something like that. To get the observed minus expected, because we're going to square here, it doesn't really matter if you do E minus O or O minus E. I got this. Now, this in and of itself is not that useful because if I just add all of these up, I'm going to get 0. So to deal with that, what we do is we square all of those numbers. And then, so we've got now the observed and expected squared. And since it's squared, it doesn't really matter which one goes first. I realize I have it backwards here, my bad. And then what we're going to do is we're going to divide each of the values by their expected. So 49 over 20, 64 over 20, etc. And then add them all up, right? The symbol just means add everything together. And what I get is a number of 11.3. That is my chi-squared statistic. And it doesn't mean much until I look back at that graph. Now notice I have 5 degrees of freedom here because there were 6 numbers. So if I knew that the total was 120 and these were the results I got for the first 5, I could figure out what that last one is. So I have 5 degrees of freedom and the number I'm kicking out here is 11.3. So now let's look back at that graph. Okay, so I have this and we've got 5 degrees of freedom. I set R, so like that line at 11, and you'll notice that that is at 5%. So my 11.3 is going to be a little bit to the right of this, which means that this is a statistically significant result, right? It's kind of right on the border there, but in a world where this is a fair die, this is only going to happen, this result is going to happen 5% of the time or less. So it's a pretty unusual result. Now, I will say that this is rounded pretty far, so you might want to actually use a calculator to do this. And so I'm going to show you what that would look like. The actual p-value that we should get is 0.457. And this is what it's going to look like on your calculator screen. I'm not going to go through the calculator instructions right now because you can get those on the Google Classroom. They're attached to your homework assignment today. So we've got our chi-squared value. It came out as 11.3. Here's our p-value. That's the probability of this thing happening. And notice I did have it set at the degrees of 5. Don't necessarily have to worry about this part. The other option, if you don't have a calculator, you could do this with Google Sheets. This Google Sheet is also attached, and you'll notice it's the same kind of deal. I did give us a different result here in yellow. You'll notice I have a far more expected result, closer to the actual expected values, but then I did subtraction, I got the squared, I did this, and then this here, you'll notice, hang on one sec, the chi value that I have here, which is just a half. Here's the formula. It literally just added up B6 through G6. So I literally just added up B6 through G6. So I'm just summing those. That's how I got the chi value. And then over here, the chi test, this was me just kind of giving you, instructions for how to get there, is you would type in equals chi test and then the range of the observed, the range of the expected. That's what this formula bar is right here. We're here at B2 to G2, so that's B2, so all of the yellow, and then G2, these are the expected, and then it is calculating the probability. Now here in a far more likely scenario where you have about 20 of everything, this happens 99% of the time or less, a very expected result. This video is already pretty long, so I'm going to probably call it here. There are instructions, an example of the two-way table in your book. By all means, come ask me questions if you have them. Let me know how things are going.